This is Richard Terrile from the Jet Propulsion Laboratory for another Galileo report. Status of the mission: Galileo is healthy. It's now 2 hours and 25 minutes since its closest approach with the planet Earth. It's at an altitude of 81,010 kilometers, that's 50,337 miles, and is traveling at a speed of 9.4 kilometers per second, or 21,126 miles per hour. Joining me are two interdisciplinary scientists on Galileo, Carl Sagan and Andy Ingersoll. Welcome, gentlemen. Glad you could make it. Well, we've flown past the Earth and we've gotten a first quick look at the Earth. We'll have more looks in the next week or so. But let me ask you, what is the significance?
Well, I think the first thing to bear in mind is that all the data obtained and to be obtained about Venus, the Moon, and the Earth are all gravy. If we got no such data, the mission still has its objective before it and everything's going well. But having said that, it's clear that both for the Moon and the Earth and for Venus, there's important new data that will be obtained. In the case of the Earth, of course, it's loaded with Earth satellites that are looking down on it. You might think that there'd be no chance that a quick flyby by such a spacecraft would obtain anything new, but there are a bunch of things that it will obtain. One of which that Andy Ingersoll and I have both been involved with is the construction of a movie which will show the Earth rotating before us, sitting in the blackness of space. One that we didn't get but hope to get next time is shows the Earth there and the Moon going around it in a stopped motion movie. There will be a zoom. Pictures will be taken in a time reversed sense, but what we will eventually see is a picture like the one that has just come through of Australia, and then the spacecraft backing off, and a very nice setting of a perspective of one area in Central Australia in the context of the entire Earth. We will be looking in a way that has not been attempted before with all those Earth satellites for vegetation over the Earth. You had Reed Thompson talking about that. It's a wide range of interesting things. We're looking for the ice cover in Antarctica. There's a lot of science that will come out of this.
I think what's interesting is that we're all very familiar with what we have here on Earth, but not many of us are very familiar with what an interplanetary spacecraft can do. This really gives us a very good perspective, a good self-calibration as to what kind of information we're going to get.
It is a first, after all. First time a spacecraft, one of our spacecraft, has come zooming in from outer space to look at us. And I think it has some philosophical significance for that reason. Makes me appreciate how vast space is and the universe is, and how protected we are from it by our little thin atmosphere. Apparently, Galileo's traveling so fast that if you were standing next to it when it went by, you wouldn't even see it because it's going so fast. And the other point is Galileo's having trouble really seeing us. It can't photograph us. We're isolated from the rest of the universe down here. To me, that's very significant.
I think it's a very interesting mental exercise to imagine yourself the controllers of the Galileo spacecraft, except you live somewhere else. Okay, imagine Galileo is a spacecraft from somewhere else in space, and it's making this extremely quick pass by the Earth, all instruments recording. What about the Earth would it detect, and what fraction of that would be what we consider important about the Earth? Would it detect that this is an ocean planet? There's no other ocean planet in the solar system. Would it detect life? Would it detect intelligence? Those are three interesting questions, and I think the answer to all three is going to be yes, that it will detect all three. The question of intelligent life, highest resolution pictures are only a little less than a kilometer resolution, finest detail you can see, in Central Australia. Maybe we'll find some sign of life there, maybe it'll be a highway or something, but by no means guaranteed. On the other hand, the plasma wave instrument has a set of channels. You can imagine it plotting against time the frequency of radio emissions from the Earth. And down at the low frequencies, much of that can't get out because of the plasma frequency of the Earth's ionosphere. But then above that, it can get out. And now Don Burnett is beginning to see a set of regularly spaced emissions at a fixed frequency, which almost surely is some military radar system or something like that. And as we look more, I'm sure we'll find.
And they have a 24-hour period, and they keep reoccurring. And
that as well, but on a finer modulation timescale, there's the actual content of the radar system or radio transmission.
So if we really knew what these things were, we could deduce that there was intelligent life. But the real question is, the first thought we might have is there some natural phenomena?
Sure, you do that always.
There's a lot of circumstantial evidence. There's a fact that that oxygen will be readily detected in great abundance.
The oxygen A band at 0.76 microns, there's a filter sit right on it. It will be detected. Now, of course, you could argue that that comes from photodissociation of water vapor and escape of hydrogen. And then the question is there so much oxygen? There is, that you can't attribute it to that source. Then there's the fact that other atmospheric constituents, like methane, are in wild thermodynamic disequilibrium with this excess of oxygen. The equilibrium amount of methane is 10 to the minus 35 or something like that, and the actual amount is something like a part per million. And so that means that there's a constant source pumping methane into the atmosphere. It immediately gets oxidized to CO2, but then there's more of the steady state equilibrium. You might suspect that that's due to biology. Then there's the chlorophyll signature in the red, this very steep cliff in the red reflection spectrum,
now,
which
is that
maybe we
signature,
will find.
Is that chlorophyll signature unique, or could that be
If
some
you didn't know about
mineralogic-
chlorophyll, suppose you come from a planet where they got something else, then all you would deduce is that on this planet there's a kind of pigment that absorbs in the red and then has a very sharp diminution to nothing. And then at longer wavelengths, whatever this material is has a lot of fine scatterers that reflect light back. And then your problem would be to figure out some geological explanation, and then only in the absence of all other alternatives would you entertain the hypothesis that this is due to biology. But it's not a distinct signature of life.
You would see the spatial distribution of that chlorophyll, and you'd begin to suspect that maybe it liked the land and
That's right. And periphery of the land, and not deserts in the center.
The edge of the ocean basins,
Yeah,
and you'd
but you
say,
know,
this is quite a pigment. you'd say
Absolutely.
to
But
yourself.
scientists would be very clever in inventing alternative explanations.
We always are. Do you think that this encounter is going to impact the second encounter? We can learn something here that we might check out in the second encounter.
No question.
I think we're going to be able to make some very nice images during the second encounter. I think we're going to do some nice atmospheric comparative planetology during this mission. Trot out some of the standard products that planetary scientists are not paying any attention to, just weather movies, and maybe take our planetary weather movies from other planets, Venus and Jupiter, and I think we're going to get the two groups and the two data sets together for the first time. And we could have done it without Galileo's flyby, but somehow these events precipitate good science.
Well, it's interesting now to have the two twins in the solar system, Earth and Venus, both recorded by the same spacecraft. And that's an interesting comparison. They're two very, very similar planets, at least in gross size and density, but they're very, very different in terms of their atmospheres.
Yeah, you know, I've always thought that if you were an extraterrestrial and you came upon these three planets, Venus, Earth, and Mars, you'd say, well, what's that funny one in the middle? It doesn't have any carbon dioxide. That's the big absence.
Where did it go?
Yeah, where's all the... Well, I wonder if you'd figure out where it's lying, that it's down in the sediments. Would you figure that out?
Well, you'd probably look for the 2.3 micron carbonate feature and see if you could find it. And there'd be little places, Dover in England, and a few other places where you'd see a lot of that, and you'd wonder if there was a vast sedimentary column in which the carbon dioxide is locked away as carbonates. And then you'd have to ask, how come that's the case on the Earth and not on Venus and not on Mars? I think that would be a lot tougher to get the amount of CO2 in the carbonate column down many kilometers from remote observations. Maybe there would be a way for an advanced civilization to do that.
The ocean is fairly easy to detect because there's basically no topography on it, but could we deduce the composition?
Here's the way I say it would be done. If you could take a thermal map of the Earth in daytime and at night, okay, so you'd need 2 flybys, or a short-lived orbiter would do that. Then you would find a certain high temperature of the land in daytime, a lower temperature of the land in nighttime, and virtually no temperature fluctuation of this other stuff. So it has a high thermal inertia and it's smooth, as you said. And then you'd have to think what material could satisfy those criteria. Now it turns out, as Moose Shaheen has stressed to me, that silver satisfies those criteria. And certainly a planet which is mainly covered with silver would be of great interest. But silver has a very low cosmic abundance. And looking through your list, you would find water, which has a very high cosmic abundance, satisfies those criteria as well. You'd find water vapor in the atmosphere. You would know the albedo of the planet. You would know its heliocentric distance. You could calculate what its equilibrium temperature ought to be with carbon dioxide and water vapor. You could calculate what the greenhouse effect is, so you would get the actual temperature of the Earth, and sure enough, that would be within the liquidus range of water. So you would say, this has to be water. I think you'd get it right off.
I think you'd get it too. Consider the sulfuric acid on Venus. We, as a community, figured that out without ever seeing the spectral signature of sulfuric acid. It was just a question of what could form round droplets at those temperatures, and the droplets had to have a certain index of refraction. And looked through the handbook, and there it was. Sulfuric acid was the only thing.
Yeah, the key data there was the polarization phase curve of Venus. And so all you had to do is just measure to a precision of about a part per thousand the polarization of the sunlight reflected by the whole disk of Venus as a function of the phase angle.
There's nothing else that it could have been on Venus, and nothing else that could be that ocean stuff on the Earth.
So I don't think an advanced extraterrestrial civilization would have any trouble figuring out the basic stuff about the Earth. Maybe intelligent life would give them a moment's pause.
A moment's pause. And the biosphere itself, it takes a little bit of deducing. You probably have to rule out a lot of other things first.
Yeah, I think that's absolutely right. But probably the strongest argument from a very superficial look would be what I was talking about with methane and other gases, this wild thermodynamic disequilibrium. Things that shouldn't be there, they are there. They should be oxidized in a flash, so they must be made at a great rate. And could you possibly explain their production rate in order to get this steady state abundance by non-biological processes? And there again, I suspect the scientists would be very inventive, but it would be really pushing to get all of those. Nitrogen might not be so easy to discover, but that's not such an important issue.
Let's look forward a little bit toward the Jupiter encounter. We've got a spacecraft which is now instrumented differently than Voyager. We all worked on Voyager, but we now have the NIMS experiment and, of course, the probe. What do you think of the fundamental things that we're going to do at Jupiter that Galileo could provide us with?
Well, we've got the probe, so we're going down into the clouds and sample the composition, sample the temperatures and the winds. Jupiter may have the closest chance we have to sample what the whole solar nebula was made out of before there were planets. So that's a major advance. We've got an orbiter, so we spend 2 years there going around watching everything change.
Now that's very important because
and
we
go
know
screaming by those satellites at incredibly high resolution. That's going to be spectacular.
And the Jovian magnetosphere, biggest in the solar system.
Having the orbiter is
You know, we know that Jupiter and the moon Io and the magnetosphere and a lot of the conditions do change with time, and that getting that snapshot with Voyager was very, very intriguing. But it's very important to get the whole perspective.
For me, there's so many exciting things about Galileo and Jupiter, but the most exciting thing is to have, as Andy says, an entry probe going into an atmosphere of a Jovian planet. Never before in human history has anything approximating that been done. And for me, absolutely key question is, what is the chemistry as a function of depth? Is there a lot of organics there? Is it sulfur chemistry? Is it phosphorus chemistry? What's responsible for all those colors? What about that water cloud layer at room temperature and a pressure of a few bars? That's a very interesting environment.
Yeah. All the years of speculation, nothing beats actually sticking an instrument in there.
It's a great thing about science.
That's great. Well, thank you very much, gentlemen. I really appreciate your coming here. Currently, the status of Galileo, 2 hours and 45 minutes past its closest approach. It's 92,233 kilometers above the surface of the Earth, 57,311 miles. Galileo is traveling at 9.3 kilometers per second, 21,000 miles per hour. We have a little film clip of how the spacecraft was deployed, and we'll show that. It begins with the now familiar launch on a space shuttle. That launch occurred October 18th, 1989.
Guidance confirms a good roll maneuver.
And the Sunnyvale flight director has just confirmed the successful deploy of the inertial upper stage and Galileo. Galileo reports positive telemetry of deploy. Also, we see the orbiter performing a minus X translation maneuver to move away from the IUS Galileo stack.
Time, Houston. The spacecraft is stable. Galileo is on its way to another world. It's in the hands of the best flight controllers in this world. Fly safe.
In the blackness of space. One that we didn't get but hope to get next time is shows the Earth there and the moon going around it in a stopped motion movie. There will be a zoom. Pictures will be taken in a time reversed sense, but what we will eventually see is a picture like the one that has just come through of Australia, and then the spacecraft backing off, and a very nice setting of a perspective.
Welcome, gentlemen. Glad you could make it. Well, we've flown past the Earth, and we've gotten a first quick look at the Earth. We'll have more looks in the next week or so. But let me ask you, what is the significance?
Well, I think the first thing to bear in mind is that all the data obtained and to be obtained about Venus, the Moon, and the Earth are all gravy. If we got no such data, the mission still has its objective before it, and everything's going well. But having said that, it's
This is Richard Terrile from the Jet Propulsion Laboratory for another Galileo report. Status of the mission: Galileo is healthy. It's now 2 hours and 25 minutes since its closest approach with the planet Earth. It's at an altitude of 81,010 kilometers, that's 50,337 miles, and is traveling at a speed of 9.4 kilometers per second, or 21,126 miles per hour. Joining me are two interdisciplinary scientists on Galileo, Carl Sagan and Andy Ingersoll.
It's clear that both for the Moon and the Earth and for Venus, there's important new data that will be attained. In the case of the Earth, of course, it's loaded with Earth satellites that are looking down on it. You might think that there'd be no chance that a quick flyby by such a spacecraft would obtain anything new, but there are a bunch of things that it will obtain. One of which that Andy Ingersoll and I have both been involved with is the construction of a movie which will show the Earth rotating before us, sitting